So the last speakers of this conference, this session and also conference is Professor Mariana Haragus, yes.
Yes.
She is talk about spectral approach to transversal linear instabilities of line periodic water waves. So please start.
Okay, so thank you for the introduction, and also thank you very much for inviting me to give a talk in this very nice workshop. So thanks to the organizers, and also thanks for the careful organization. And I'm really sorry about these problems with my computers, which are not, well, it doesn't work always very good. So, well, my talk today will be actually like the previous two talks. I'm going to talk about a stability problem. It's just that the problem will be in the context of water waves, so a hydrodynamic problem without viscosity. So I'll remove viscosity from the talks before, and I will focus here on analysis. So it will be analysis and stability of periodic waves. So as I said, I'll remove viscosity. So the problem I'm interested in is the so-called water wave problem, which is also a classical problem in hydrodynamics. You can see a nice picture here. So actually this is concerned with the flow that one can see on the sea, for instance. This is the nicest example I would think. And as you can imagine, then you have a lot of waves there which are formed. So in my talk here, I will focus on periodic waves. You see here some periodicity in these waves. So more precisely, the mathematical problem is concerned with a three-dimensional inviscid fluid layer of constant density, so no viscosity, under the action of two forces. So we only have gravity and surface tension, so a force at the surface of the liquid. And the flow also, I suppose it to be irrotational. So it's really the classical water wave problem. A few words about the equations. So I won't insist much on the exact form of the equations, so more on the methodology and on the problems. So the equations describing this hydrodynamic problem are the Euler equations, so-called Euler equations, where we find Laplace's equations inside the fluid domain. So here I use non-dimensional variables. So the free surface lies at a height, medium height of 1 plus a perturbation eta, which actually depends on, well, x, z, and time t. And as you may notice from here, I have not the standard notation for the Cartesian coordinates. In my Cartesian coordinates here, y, it's the vertical coordinate. And then x and z, this will be important, are the two horizontal directions. Okay, so inside the fluid domain, then we have Laplace's equation, which is nice and linear, so it shouldn't be so difficult. But the problem with this is that we have this free surface here, eta, which is a function itself. So as you can see from the problem, this is something which varies in time and space. It's not constant at all. And then we have to impose boundary conditions. And boundary conditions, you can see them here. There are two types of boundary conditions. These are kinematic boundary conditions, which actually define the fluid domain. So saying that the fluid stays inside precisely this domain. So this one, it's at the bottom, which is at y equals 0. And this one, it's at the free surface. And then a third boundary condition, which is, I would say, the worst one, that you can see here, which is the Bernoulli equation written here in non-dimensional form, as I said. So actually here the length, I think, for is the fluid height is the length for space, and then there is a velocity c in the direction x of the wave. So we assume waves move in this direction. So the velocity c in this direction is a scale for velocity. So then in this setting, so in this equation, you see here in the last Bernoulli equation, we find here actually two parameters, alpha and beta, which is written here. And this is the important message to remember from this equation, I would say. So in these two parameters, we actually find all physical parameters, fluid density, gravity constant, surface tension constant, and height of the fluid. Okay, so these are the two important parameters here. Now, what are the difficulties in this problem? Actually, there are two main difficulties here. Of course, as you can imagine, the first one comes from the fact that the surface is free. So we have this fluid domain, which is unknown. So we have a variable domain. And the second one is, of course, because we have these boundary condition, and in particular, the second one, which are non-linear. So these are mathematical difficulties. If you want to do analysis, they pose you a lot of problems. On the other hand, what is very nice about this problem is that it has a very rich dynamics. This is something you can also imagine when you just look at the sea. You see plenty of waves there. So there are a lot of waves there. And there are a lot of symmetries in this problem. What is very important, there are several Hamiltonian structures. I will mention at least one in my talk later. And there are a lot of many particular solutions. And in fact, in this context, perhaps the best known particular solution is Russell's solitary wave, which is a localized solution in space. And of course, then there are some more nasty solutions which look like tsunamis and so on. But in this talk here, I will focus on periodic waves. In fact, two-dimensional periodic waves, when the free surface looks like here, like this plot, it is periodic. So this will be my x-coordinate here. And it will be periodic in x. And the solutions will be constant in z. As I said, z is my second horizontal coordinate. And these are traveling periodic 2D waves. And the problem I'm interested in their stability. So we already have seen some talks on stability. The question is the same. It's just that here I will focus on a simpler question. I will focus just on the question of linear stability. And I wrote here instability because, as we will see, well, most of these waves will actually be unstable. So I focus on linear instability. But in contrast to the previous talks, I'll add a dimension. What does this mean? This means that I will look at what is happening with this two-dimensional wave when perturbations are also allowed in the direction z that I call transverse direction. It's the direction which is transverse to the direction of propagation. That's why transverse linear instability. And as I mentioned at the beginning, I focus just on analytical results. There are plenty of numerical results. I'm sorry, I won't talk about this here. And my main interest is to obtain these results for the Euler equations. But as we will see, these results are very good predicted by long wave models. So this will be part of my presentation. So this is a plan of my talk. And first thing to recall, because I won't discuss the stability problem, the existence problem, sorry. So the existence of 2D periodic traveling waves. Here are the waves. In fact, there is a huge literature showing or studying these existing questions, and there are a lot of results. Here is a list which is non-exhaustive at all. And as I said, there are a lot of results on periodic waves. What I'm interested in here in my talk are on the periodic waves which exist in the blue shaded region here. So what do I have here? Here I have, remember I said from the governing equation, just remember my two parameters, beta and alpha. Beta actually stands, I forgot to say, it's proportional to the surface tension. So this means that beta positive will really have gravity capillary waves. Pure gravity waves, they are here when beta is 0. So in this parameter plane, beta and alpha, I will focus on this blue shaded region where there are, as I said, a lot of existence result. And as I said before, well, perhaps the most known, better known solutions in these water wave problems are localized solutions, as Russell's solitary wave, which was discovered a long time ago and has a very long history, fascinating history, but it's not the point of my talk. These waves, well, in some context also called Stokes waves, they go back to Stokes, also in the 19th century. These are the waves I'm interested in here for the stability problem. Okay, now a few words about transverse linear instability. So as I said, transverse means we look for perturbations which also depend on the horizontal transverse direction, which is Z. So my Z is still here, X is still here. I won't write it again. And of course, they depend on the longitudinal direction X. And in fact, as we have seen in the previous talk, if we look at periodic structures, at periodic waves, there are several classes of perturbations in this longitudinal direction X, which are important. The simplest one is the class of perturbations which are periodic. So there is a sketch here where the blue wave, which is my traveling wave, is perturbed periodically. So it's like imposing periodic boundary conditions to our problem. And these are also called co-periodic perturbations. The reason is that there are some other periodic perturbations which are also periodic, but they do not have the same period as that of the wave. Here we perturb with something, not every period, but let's say every 2 periods, every 3 periods. So such perturbations are called subharmonic perturbations, and they have a period, so they are also periodic, but not with the same fundamental period as that of the wave, but with a fundamental period which is twice, 3 times, and so on, the period of the wave, or more generally, an integer multiple of the period of the wave. And finally, there are the localized perturbations, or more generally bounded perturbations that we have seen in the previous talk. And actually, this is the most challenging part of the analysis. Well, now, as I said in my talk, I will focus on a slightly easier problem, well, not slightly, on an easier problem, to be honest, which is the instability problem. Now, from the instability point of view, it turns out that instability with respect to coperiodic perturbations Of course, it implies instability with respect to subharmonic perturbations, because these are part of these perturbations. And it also implies instability with respect to localized perturbations. So in my talk here, I will focus on perturbations which will be bounded, in fact, periodic in Z, and also periodic, coperiodic in X. So now a few words about predictions, because, well, these Euler equations, you have seen them, it's difficult to get an idea of what to expect just from when looking for these equations. And long wave models, which are obtained, derived formally or more rigorously, there are a lot of recent works justifying such long wave models. They often give a very good prediction on what is happening in the full problem, at least at leading order. And in particular, it turns out that for this transverse linear instability problem, they indeed give good predictions. So as I said before, I focus on perturbations which are coperiodic in X and periodic in Z. So this is, let's say, the smallest class of transverse perturbations. And if we have instability in such a smaller class, of course, this will imply instability in larger classes of perturbations. And such long wave models are derived in particular parameter regimes. These are the parameter regimes in dark blue here in this diagram. And more precisely, the model equations depend on the parameter regime. So first regime, which from a point of view of analysis is actually the simplest one to analyze, if something can be simple with the Euler equations, is the regime of large surface tension. Remember I said beta is proportional to the coefficient of surface tension, and in non-dimensional parameters, this means that beta is larger than 1/3, and we are close to an alpha close to 1. So in this case, the model equation is the so-called Kadomtsev-Petriashvili-1 equation, which is a two-dimensional version of the KdV equation. If you remove here the term in U, YY, and actually the Y here should be a Z, sorry. This term in U, ZZ, and one X derivative here, you just have, you remove this, this, and this. What it remains is the KdV, the well-known KdV equation, which is a model for two-dimensional waves. KP equation, shortly, instead of Kadomtsev-Petriashvili, it's a model for the three-dimensional waves. And it turns out that for the KP, and this is the so-called KP1 equation. At the end of the talk, I'll perhaps have time to say something about KP2. So in the context of KP1 equation, there are several results listed here showing that actually, indeed, periodic waves are transversely unstable. And also, some years ago, I considered this problem for the Euler equations. Now, a second parameter regime is the one here when we have, well, weak surface tension, this beta in this parameter regime is less than 1/3. Then a model here is the Davis-Stewartson system, which is written here with the same mistake as before. Y should be replaced by Z. And here also. And it turns out that also here, periodic waves are transversely unstable. Finally, a more complicated model, which arises close to the critical point here, beta equals 1/3, in a small parameter regime here, is a fifth order KP equation, where in a recent work with Eric Valen, so some years ago still, we have also showed that periodic waves are linearly transversely unstable. So actually, so far, all predictions given by the model equations in these parameter regimes show that periodic waves are linearly transversely unstable for gravity capillary waves. Now, how about the Euler equations? So it turns out that there is a common approach, in fact, a general criterion, instability criterion, which allows to recover all results that I've mentioned you before, at least for the model equations. So this approach is an abstract criteria from instability obtained some years ago by my PhD student Cyril Godet, which was extended to the case of the Euler equations in a work by Mark Grove, Xiuming Sun, and Eric Valen, almost in the same year, and actually which goes back to a joint work with Mark Grove and Xiuming Sun, well, some 20 years ago, actually 20 years ago, where we studied the transverse instability of solitary waves. There were no periodic waves there, but solitary waves. And it turns out that all these results, they can be obtained using this abstract instability criteria. Now, what is this criteria? The idea, the starting point of the analysis concerns in rewriting the stability problem, not as an evolutionary problem. So usually you write it as an evolutionary problem. You have, let's say, Vt equals f of u, and it's what we also saw in our talks, in the talks before. But to write it in a different way, as an evolutionary problem, or as a first order problem, not in time, but in space. By taking the transverse direction here, z, as evolutionary variable. So this is the starting point of this type of this criterion, is to write the equations in such a form, first order system with respect to the transverse direction, then some term, typically we have something dut, which still is linear in time, at least for the Euler equation, and then some nonlinear map here. One advantage of this problem is that, as I said, this is the formulation which we use for transverse instability. One advantage of this formulation is that then a periodic wave, also a solitary wave, in fact, which does not depend upon Z, is then an equilibrium of this system. This is a dynamical system, and my periodic wave is an equilibrium of this system. It is also independent on T. Okay, so this is the starting formulation. Then what does it mean, transverse linear instability, in this formulation? Well, the definition is the usual one that one uses for linear instability. Roughly speaking, linear instability means that the linear problem possesses solutions which are with exponential growth. So here, this means, in this context, this means that my periodic wave is transversely linearly unstable if the linearized system, here is my linearized system, where I denote by L the linearization of f at u star, possesses a solution which is exponentially growing. I have an exponential factor, lambda t, with real part of lambda positive, and V lambda is some bounded function. Then I say that the wave is transversely unstable. And this bounded function in my talk here, in the results we obtain, and actually for all other results, it will be periodic in X with the same period as the wave, and also periodic in Z. Now here are the hypotheses of the general criterion. So there are three hypotheses, rather simple. First hypothesis is that we have a system, a dynamical system here, which is reversible, it is important to say, in Z, of course. This means that we have a symmetry which anticommutes with D and F when which anticommutes with D and F in the dynamical system. Or more intuitively, this means that in our original problem, we have a reflection symmetry in Z. We can reflect solution in Z, which is true for the Euler equations and actually for a lot of hydrodynamic problems. In particular, for instance, we have something like this also in the Taylor-Quade problem, in the Rayleigh-Benard problem, and so on. Then the second hypothesis, this is the key hypothesis actually, is that the linear operator that I showed you before, it's the linearization of this 2D wave. So this is a differential operator with periodic coefficients. This linear operator possesses a pair of simple purely imaginary eigenvalues. In fact, the criteria holds also when instead of simple, we say odd, not a pair. Instead of simple, we say a pair of purely imaginary eigenvalues with odd multiplicities. So this is the key hypothesis. And then there is a technical hypothesis, which is mainly here to allow us to use perturbation arguments in a rigorous manner, saying that, well, we have the operator L here, we have also the operator here, that both are closed in some space of functions, and D, it's a relatively bounded perturbation of L, so written here. So these are the hypotheses. Let's say main hypothesis, reversibility in Z, and this pair of purely imaginary eigenvalues, simple purely imaginary eigenvalues, but it also works for odd purely imaginary eigenvalues with odd multiplicity. Then the general results says that indeed under this hypothesis, the linearized system here will possess a solution which is exponentially growing in time, with the lambda here, which is actually real sufficiently small. So in particular, there are values lambda positive sufficiently small for which we have such solutions. And this, of course, then implies that U star is transversely linearly unstable. Now, a few words about the proof, which is actually a very simple proof, is, well, what do we have to do? We have to look for the solution of these linearized systems of this form. If I put this ansatz here, this means that since I have no t dependence here, the t derivative will be replaced by multiplication by lambda. It's like in eigenvalue problems. It's just that my eigenvalue lambda now, it's not the eigenvalue I'm going to talk about, but this is a temporal eigenvalue. Is sitting here in the right-hand side of the equation and not in the left-hand side of the equation. This is again due to our particular formulation. Okay, so what we have to do, we have to look for periodic solutions in Z of this equation. Well, equivalently, this means that the linear operator here, in the right-hand side, we have a linear operator, possesses two complex conjugated purely imaginary eigenvalues. Of course, if I have a purely imaginary eigenvalue, well, this means that I have solutions of the form e to I k z times something. And these are solutions which are periodic in Z. Now, how to find these purely imaginary eigenvalues for this operator? And here you can see where our hypotheses can come from. Remember, one of the hypotheses was that L possesses two simple eigenvalues, pi minus ik star. So I know I have two simple eigenvalues here. My lambda will be small, so I want to make a perturbation argument here. One just has to be a little bit careful. First, in order to do this perturbation argument, of course, I need that this operator is a small relatively bounded perturbation of L. This will tell us then that when adding lambda d, my eigenvalues will stay in a neighborhood of these two eigenvalues. But I have to make sure that they won't move off the imaginary axis. And here is where the reversibility hypothesis plays a role, because of this reversibility, the spectrum of this operator is symmetric with respect to the imaginary axis. Together with the fact that my operators are real, if lambda is real, then it is also symmetric with respect. Well, here I was a little bit too fast when I wrote this. So perhaps I read it again. So reversibility implies actually that the spectrum is symmetric with respect to 0. Or in other words, if lambda is an eigenvalue, let's say mu is an eigenvalue, then minus mu, it's also an eigenvalue. I have a symmetry with respect to the origin. Together with the fact that my lambda is real, I have the operator, which is a real operator, so its spectrum is symmetric to the real axis. These two together implies that we have a symmetry with respect to the imaginary axis. Now, if my eigenvalue is simple, it stays close to the imaginary axis. Simplicity implies that it remains on the imaginary axis, purely imaginary, for small values of lambda. So this is the proof of this abstract general criteria. Now, how does this work for the Euler equations? And in fact, the results here are some very recent results with Tien Trong and Eric Wallen on the Euler equations. So, as I said, the starting point is a formulation of the problem in this form. I won't say much on this here because this is one technical part when you work with the Euler equations. Nevertheless, such a formulation is well known, they are well established. There are several formulations like this. First one going back to a work by Groves and Mielke 20 years ago also, and then there are other formulations, most recent one in the work that I already mentioned by Groves, Sun and Wallen. Okay, so we have a formulation in which we have a big problem. As I said at the beginning, these are the boundary conditions. So I won't comment on this problem in this talk. I will only say, well, this is a problem, it's a technical problem, but I won't discuss it in more detail than this. I will just say, well, it's a technical, difficult problem, but we know how to handle it. And we learned this also from this paper from Gross and Mielke. So we have a Hamiltonian formulation for the Euler equation. The fact that it is Hamiltonian, it is actually important here because this already gives us the symmetry of the spectrum that we need in our hypothesis. Okay, and then in the work with Tien and Eric, we focus actually on this parameter region, which is in dark blue here. So this is a region where we don't have model equations, but we have the predictions that, well, in all model equations that we considered, periodic waves were transversely linearly unstable. Now, in this region, one can show that fixing alpha and beta here, any fixed beta and alpha in this region, we have a family, a one parameter family of periodic waves. So this is the free surface, this is the velocity potential, parameterized by a small parameter epsilon, such that, so these are periodic with a wavelength, wave number k epsilon, close to some k star. Actually, this is a solution of the dispersion relation. I won't have time to enter into connections here with this in this talk. So just what it is important to remember, we have this one parameter family for small epsilon. And we know an expansion, actually one can compute explicitly the expansions here of these periodic waves. So for each beta and alpha, I have this one parameter family for small epsilon. They are smooth in epsilon, so we can use expansions. And this is the family that we want to show that the waves are linearly transversely unstable. Okay, how to do this? Of course, as I said, well, we apply the criterion. So we have a formulation. Next step, we consider the linearized problem. And again, these boundary conditions, which will always bother us in this when analyzing the Euler equations, that I won't mention again. So what is this linear operator? So we have the wave before. U epsilon is actually the solution in this formulation, the waves written in this formulation. We have a nice space of functions of 2 pi periodic functions. Actually, here I have hidden a step, a rescaling of the period to 2 pi. So we have our linear operator. We can write it explicitly. So here are the explicit formulas for these linear operators. You can see these are matrix linear operators. But what is important to remember from this part is that we have a leading order part in this operator, which is the operator and epsilon equals 0. This is a differential operator with constant coefficient. And then we have a perturbation, which is order epsilon, which are all these terms here, quite long, but which are small in epsilon, which are due to our periodic waves. Okay, and what do we have to do? Main step is to show that the operator I showed you before possesses a pair of simple eigenvalues for epsilon sufficiently small. Why this is the main step? Of course, well, we had a technical check that operators are closed and so on. This comes from the formulation. If we have a correct Hamiltonian formulation, this is a consequence. And then we have the hypothesis on reversibility, which is in this case satisfied because we have a reflection in Z of our hydrodynamic problem. Okay, so how to find this pair of simple eigenvalues? And now again, I will mention the previous talk. Well, we will use perturbation arguments. The good point here, and it is a very good point when you work with periodic waves, you have all these operators that I haven't said much about these operators, but they act in spaces of periodic functions. If we restrict to perturbations which are periodic. Now, if we work in spaces of periodic functions, we have good Sobolev embeddings. And in particular, we have operators with domains which are compactly embedded in the space. This implies that our operator is with compact resolvent. As I said, this is in general holds for when we work in problems with periodic waves and coperiodic perturbations. And the important consequence is that we have a pure point spectrum. So what I have to do actually, our perturbations argument is to look for perturbations of isolated eigenvalues. And I am interested here in finding a pair of purely imaginary eigenvalues. So I only have to look at the eigenvalues on the imaginary axis. And for this, of course, first step, we look at the operator at epsilon equals 0. A Dirac computation, a little bit long, but still straightforward or standard, shows that for this operator L0, we have only one purely imaginary eigenvalue. So there are no eigenvalues here except 0, which is an eigenvalue with geometric multiplicity 3 and algebraic multiplicity 6. Actually, we have associated to 0 3 2x2 Jordan blocks. And then the idea is, as in the previous talk, we use a perturbation argument. We know that, well, since our operators are not badly behaved, when perturbing, this eigenvalue will split perhaps in 6 eigenvalues, but they will stay in a neighborhood of the origin. And the main difficult part of this analysis is to check what is precisely happening with these eigenvalues for small epsilon. And the result is the following. In fact, it turns out that 0 remains an eigenvalue of the operator L epsilon. The reason are symmetries. I said at the beginning, the problem has a lot of symmetries. Here, they are really very helpful because they allow us to show that actually for any epsilon, 0 will be an eigenvalue with geometric multiplicity 2 and algebraic multiplicity 4. So 4 dimensions stay here at 0. And then we only have to compute 2 dimensions. Well, I won't show you the computations because they are really long, as usual for the Euler equations. But the result is that we have indeed a pair of simple eigenvalues for sufficiently small epsilon. This shows that our main hypothesis is checked, and by the general criterion, we can conclude on transverse linear instability in this region. Next, there is another region, the dark blue region here. The analysis stays the same, but there are some differences, not from the point of view of the strategy, but from the point of view of results. Also, computations are similar. So what is happening in this region here? Well, in this region, it turns out that we have two one-parameter families of periodic waves. Before, we had one parameter family with wave number close to some k star before. Here we have two families with wave numbers close to two numbers, kappa 1 and kappa 2. And perhaps I should say at least now that, in fact, this basic wave number, this is a solution of the dispersion relation for the linearized Euler equation, so in the water wave problem. And the difference, the fact that we have here two parameter families, two one-parameter families of solutions, is that the dispersion relation for the Euler equations for the water wave problem has in this region two solutions. So then we find similarly, we have, instead of one family, we have two families. And we can again apply this criterion. The result is slightly different. It was a little bit surprising, is that we have a red curve here. Actually, this red curve is the, also called a 1-2 resonance curve, is the curve where actually kappa 2 here is twice kappa 1. So if we are to the right of the red curve, so in the region here, both families of periodic waves are transversely unstable. But if we are to the left of this curve, we can only conclude for one family of these periodic waves. More precisely, we can only conclude for the family with the larger wave number. And the reason for this is that, in fact, for this family, it turns out that the two eigenvalues, which are purely imaginary here, for the second family, they will be real. However, this doesn't mean that we don't have instability in this case. This only means that our criteria does not tell us that the waves are unstable. But waves can still be unstable. We cannot conclude that they are stable neither. So this is a situation where we don't have this hypothesis. This hypothesis is not satisfied, so we cannot conclude. But still we can conclude in the entire region, at least for the family with the largest wave number. And now I think I have some more minutes, 4 minutes.
Yes, 3 minutes.
3 minutes. Okay, I think I have 3 slides. So just to comment on some other periodic waves. So just a few comments in the ends and some related problems. So actually, as I said before, we had model equation which predicted us that periodic waves are transversely unstable here. This general method also applies in this region. It's just a matter of, well, I would say computations, because in this, if we are close to this, so if we are in these parameter regions, it turns out that the multiplicity of the eigenvalue 0 increases. So it is at least 8 in any of this region, and this leads to much more involved computation. So this, we left this problem open for the moment. And then a few words about some related problem. I said at the beginning, the perhaps best known solution of the Euler equation, it's a solitary wave. So indeed, transverse instability for solitary waves, it has also been studied, and it was been considered actually before the one for periodic wave. And two solitary waves, which decay to 0 at infinity, are shown to exist in these two parameter regions. And in both regions, there are results showing that they are transversely unstable. The most complete results are in this region for large surface tension, where Rousset and Tsvetkov have a very nice paper already 10 years ago on nonlinear transverse instability. The result in this region is more recent, but it only concerns linear transverse instability. These are my few words about solitary waves. Another related problem is that, well, now we have an instability. One question is, what is this instability generating new solutions? And indeed, it turns out that such a transverse instability induces a bifurcation that we called some time ago a dimension breaking bifurcation, in which the periodic wave loses its homogeneity in the direction Z, so it is not constant anymore in Z. And there is a family of periodically modulated waves, which look like this, which bifurcate. And similarly for solitary waves. And such bifurcations were investigated. So there are a number of results already for these bifurcations. In the case of large surface tension for periodic waves, and then actually again in these two parameter regions from here. So these are the bifurcation, and my final remarks concern the particular case of gravity waves. Well, gravity waves means that beta is 0, so we are actually along here. And this is a big open problem. So already for the model equation in this region, which is the Kadomtsev-Petriashvili 2 equation. We had one here, we have two here. And the prediction here is that these waves are stable, at least linearly. So we have transverse stability of periodic, but also solitary waves. So the result for periodic waves is quite recent in our work, joint work with Lee and Pelinovsky for periodic waves. And for solitary waves, there are some very nice works by Mitsumashi and Tsvetkov on transverse dynamics of solitary waves, where they discuss this question from a linear point of view, but also a non-linear point of view. And I will stop here, and thank you very much for your attention.
Thank you very much. It's very nice talks. So now I want to open the question, comment, anything else. Hey, Professor Mizumachi, how about? How about you? No? So you mention names here. Okay. So I'm sorry that I am very unfamiliar with this kind of topics, but so can I imagine, so the surface waves, therefore, okay, so surface waves, there, so finally you talk about the solitary waves. The solitary waves is, its solitary waves never breaks, is it because of the surface tension?
Okay, so what I haven't said here is that my waves that I'm considering, and you can see it from the expansions, they are small amplitude waves. So I'm not looking what is happening further when their amplitude increases. Mm. So I do not say anything about breaking. I'm far away from a breaking regime.
Mm. Okay, I see. But for example, you said that you have a pure imaginary eigenvalues of your equation. Is it so? Do you have some criterion how get this pure imaginary eigenvalues?
Well, actually, if you look,
is it you said maybe assumption, but from equation or more concrete equation?
Well, the idea is that you look at to find them, you have to look at the linearized system, and you have to solve the linearized system.
Yes, I understood,
yeah. So you have no choice, actually. You cannot, you really have to go through horrible computations to show that these exist.
So as far as if my understanding is correct, then so you formulate the water waves by very much abstract functional analysis or something like that, because your starting point is the Euler equation, right? And then you have boundary conditions, of course.
Right.
Yeah. Then yeah, it's very complicated, but anyway. then from my understanding is that therefore the equation is very they fixed it, I guess. But and then I'm sorry that I'm not so aware of this kind of topics. Therefore, I'm working on, for example, similar to the Kage, then equations are fixed. And then the motion also maybe it can imagine. Therefore, maybe your result is very much natural result, and then maybe at least from the viewpoint much easier to see. But no, I'm wrong maybe. Sorry. What I want to say is that, for example, you have waves, maybe then you have bifurcation, and what appears, for example.
Okay, so what appears
maybe I'm sorry that
is what we have in this dimension breaking bifurcation.
Yeah,
so this is what appears.
Figures, yeah.
So, well, these are just plots that I made them to be nice, but as a consequence of this instability, what happens is that what appears, we have a lot of homogeneity here, and we have these double periodic waves, or for a solitary wave, you see you have periodic waves on the top of the wave.
I see. Okay.
But then the question, of course, would be, are these stable? Well, at least close to the bifurcation, they should be unstable, but I don't know, really, we haven't looked at this problem, actually.
See, so maybe what is a parameter? For example, the Reynolds number, or maybe not?
The parameter is epsilon, so it's the amplitude of the wave.
I see. So if you have very big waves, like what to say, it's a tsunami. Then
I'm far from them. My waves are very nice, so they do not harm, are harmless. Well, depends.
Okay, sorry. I'm sorry, I'm not so good chairs to ask you, but
may I ask a question?
Yes, please.
What the operator L0 is? May I ask what operator L0 is in your framework? Because
yes, it's
you made
here,
some assumptions on L0.
Here is L0.
L0. So is it a linearized operator around the periodic waves, or it's a operator with constant coefficient?
Exactly. L0 is the linearized operator, linearization around the constant flow. The constant flow, which is 0 here. So this is just this operator. And it's purely imaginary eigenvalues. If I'm looking at L0, it's purely imaginary eigenvalues are given precisely by the roots of the dispersion relation.
So it comes, the imaginary eigenvalue is an eigenvalue for constant operator. I see.
Not the ones we need for the transverse instability criterion. So this operator, it turns out that it has no non-vanishing imaginary eigenvalue. So its spectrum is actually, we only have one eigenvalue, which is sitting at 0. So there are no purely imaginary eigenvalues for this operator L0, which is here.
So with some perturbation, you get some non-zero purely imaginary eigenvalue.
Exactly. When I add the perturbation, which is here, with all these terms that I wrote explicitly here, so they are small because I don't want to talk about them, just say that, well, they depend on epsilon, they are periodic in X. because you have the periodic wave here. So these are periodic in X and small terms. Then this eigenvalue here will split in one big part which stays at 0 and two purely imaginary eigenvalues.
I see.
So in your theory, you didn't need to use something like a long wave limit or short wave limit to detect some purely imaginary eigenvalues. You just did it with some abstract framework.
Yes, actually, we remained here with the full equations. So no long wave limit. Nevertheless, the regime epsilon small means that we are in a sort of long wave regime. But one question here, because the two long wave regimes, they are, well, around this bifurcation point when, in these dark blue three regions, here we have models in long wave regimes. I don't know of any model, when I fix my beta and alpha here, of any model equation like KdV, which holds here, even for the two-dimensional problem, for long waves when I'm looking here. So this is something I don't know. I haven't seen this. And I don't know whether this is an interesting problem for people deriving model equations.
Okay.
Thank you very much.
Thank you. Thank you. Okay, so thank you very much, Professor.
Yes, and I thank you.
Haragus. I'm sorry that very short times, but maybe better to close the conference. Thank you. I would like to thank all the speakers from Tuesday and also the participants, the nice discussion and very stimulating to me, and also the people's audience. And also thank the main organizer, Professor Dr. Keiichi Watanabe. His works almost all the things. So I would like to organize these meetings next year, almost the same period. Since 2009, we are organized these meetings every year. And the next year also, we are planning to organize the same meetings. So I hope that you are participating in this conference again. So thank you so much, everybody, and then good night and good afternoons. Okay, bye-bye.